Welcome to A-Level and EP Physics. In today's lesson, we will discuss past paper questions on electric field, capacitance and Hall voltage from October-November 2022, paper 4, variant 1. As always we do, we will discuss these questions in detail so you can improve your conceptual understanding of these topics and also you can have better understanding of these questions. Let's study together, let's improve together. For question number 4, part A, we need to state what is indicated by direction of an electric field line. Let's try to understand this one with one very simple example. Imagine that we have a positive charge, so this one is a positive charge, and if we draw electric field lines around this positive charge, we will draw arrows pointing away from this positive charge, arrows pointing away. Now we need to understand, why do we draw arrows pointing away from positive charge? There must be some reason behind that. The reason is that these lines are telling us direction of force on positive point charge. So if we imagine a positive point charge is placed at this point, so this positive point charge will experience force away from this positive source charge. So these lines are simply telling us, if you place a positive charge in electric field of positive point charge, there will be force on positive test charge away from the positive point charge. So these lines simply tells us direction of force on positive charge. So simply we can say lines indicate direction of force on positive point charge. Lines indicate direction of force on positive test charge. Positive test charge. So test charge always we take positive by convention. We can also understand this one with the help of negative charge. Now imagine that we have a negative point charge. So this is negative point charge. If we draw electric field around this one and we draw these electric field lines, we will draw arrows in this case pointing towards this negative point charge. So we will draw arrow like this. So this is always we do. And this question is simply asking you the reason behind that. Now in this case also imagine that if we place a positive charge here, let's say we place positive test charge at this point. So the force on this positive charge will be through the negative charge, means towards negative charge. So if we place a positive test charge here, so this is test charge, means this is positive. So the force on this one will be towards negative point charge. So field line simply tells us direction of force on positive test charge. So simply in this case you can write down these electric field lines. Field lines indicate direction of force. So you will get 1 point. So field lines are telling us direction of force. You will get 1 mark and this is big mark. If you have written on positive charge, you will get another mark and this one will be B mark. So this is how these 2 marks will be awarded to you. For part B, it is given to us figure 4.1 shows a pair of parallel metal plates with a potential difference of 2400 volts between them. The plates are separated by a distance of 4.6 centimeters. The plates are in a vacuum. For part B1 on figure 4.1, we need to draw 5 lines to represent the electric field in the region between the plates. So first thing in this case, we need to understand the electric field between the plates. The electric field will be uniform electric field. So simply we can say uniform electric field. Uniform. So in case of parallel metal plates, electric field between the plates will be uniform electric field. Uniform. And if the field is uniform electric field, then you need to understand separation between lines. Separation between lines should be same. Separation between lines, same, simply you can say. So lines, separation between 2 lines, any 2 lines has to be the same. So separation between lines, same. So this is one thing you need to consider. And the second thing you need to understand is that electric field lines point from positive plate to negative plate. So direction of electric field lines have to be from the positive plate, more positive plate, to less positive plate. So we can say more positive plate to less positive plate. In this case, this plate is more positive. Not only positive to negative, so simply it means is from more positive to less positive plate. Less positive, or simply we say positive to negative. So these are the points you need to understand. If you have understanding of these points, then simply we can draw our electric field lines. So we can start with one electric field line here. Another one can be at this point, another one can be at this point, another one can be at this point, and other one can be like this. So these can be the possible electric field lines. So question is asking you to draw only 5, but at least you have to draw the 5, but you can draw more than 5 as well. So if I just want to draw only 5, so this is how I can draw. So these are 2 electric field lines, and the third one we can draw here, fourth one we can draw here, and the fifth one we can draw here. 5, even you can draw more than 5, at least 5 you have to draw. And in this case, the separation between the lines have to be the same. So this separation is important. You have to consider this separation. So this separation between the lines have to be almost same. So it has to be same. It's a little bit more, but it has to be almost same. So this separation has to be almost same between the lines. So if you draw this one, you will get in this case 3 marks. So 3 marks will be awarded. For the second part, we need to calculate the electric field between the plates. And we have already discussed that electric field between these two parallel plates is uniform. So simply we can say in this case E, this is equal to the potential difference between 2 points divided by the distance between those 2 points. You can take any 2 points, but in this case we will be taking 1 point here on the positive plate, more positive plate, and we will be taking 1 point on the less negative plate, because we have value of separation between these 2 plates. And also we have the potential difference between these 2 plates. Potential difference is equal to 2400 volts. And the separation between plates, between these 2 points, that is equal to 4.6 centimeters, means 10 to minus 2. Now, if we solve this one, our final answer will be 5.2 times 10 to 4 newtons per coulomb. Or you can say volts per meter. Newton per coulomb, or you can say volts per meter. These are the same units. So, in this case, we're using 2SF. The reason is that in the raw data, in the given data, the least number of SF, we have 2SF. So we are also using 2SF in the final answer. For part C, it is given to us a moving proton enters the region between the plates from the left as shown in figure 4.2. For part C1, it is given to us the proton is deflected by the electric field. On figure 4.2, draw a line to show the path of the proton as it moves through and out of the region of the electric field. So in this case, when this proton will enter the electric field, it will experience electric force. But in this case, we will ignore the effects of gravity. We will only consider electric force because gravity is much smaller than the electric force in the electric field. So that's the reason we will ignore effects of gravity. Now in this case, it is given to us the upper plate. This is more positive. So we can mark here with positive points. This is more positive, and this plate is less positive. So less positive plate we can just treat as a negative plate for simplicity. So this plate is negative, relatively negative as compared with this one. So in this case, there will be repulsive force due to positive plate, due to these positive charges on this proton. So that force will be down. And also there will be attractive force due to negative plate. So that force also down. So the resultant force, simply we can say electric force will be in downward direction. So this is direction of electric force. And proton in this case is moving horizontally. And electric force is acting downwards always in one direction. Always in one direction. So this is very similar to projectile. So if a projectile is projected horizontally in the gravitational field, so it will follow parabolic path like this, because gravity at any point is just acting in one direction. And the same is true in this case, because electric force is always pointing down in this case. So the path of this one inside the field, it has to be parabolic like this. And outside of the field, this will be just a straight line. So simply we can draw a straight line. So it will be a straight line. So this is the path of proton in the field and outside of the field. Outside of the field, simply you can draw a straight line. Why it's like this? Because electric force is just acting in one direction all the time. So this path is parabolic. So this one has to be parabolic path. So if you draw this one, you will get 2 marks. And this one has to be straight line. We are ignoring effects of gravity. So this one has to be a straight line. Let me just draw a proper straight line. So when the charge is here at this point, line after that has to be a straight line. So we can use dotted lines here. So this one has to be straight line like this. So this is how you can draw. For the second part, it is given to us a helium nucleus now enters the region of the electric field along the same initial path as the proton traveling at the same initial speed. State and explain how the final speed of the helium nucleus compares with the final speed of the proton after leaving the region of the electric field. Means simply at this point we have to compare the speed of proton with speed of helium nucleus. So we have two particles now. One particle is proton and other particle is helium nucleus. So simply first of all we can compare these two. First of all, helium nucleus. Proton has charge plus E and the helium nucleus has charge plus 2E. And the mass of proton is equal to 1U and the mass of helium nucleus is equal to 4U. Atomic mass unit. U is atomic mass unit. So the mass of helium nucleus is 4 times greater than proton, than mass of proton, and the charge on helium nucleus is 2 times greater than charge on proton. And we need to compare their final speeds. Now the first thing we need to understand, we have already discussed that in this case force acting on positive charge is always downwards. So it simply means that the particle, the positive charge in this field will be accelerating vertically downwards. But horizontal component of the speed, it will not change. It's just like projectile. So the horizontal component of velocity will not change, but vertically it will accelerate. So the vertical component of the velocity will increase. So we can calculate first of all vertical acceleration. For the helium nucleus, we can simply write down F net. This is equal to ma. Then we can compare this one with proton as well. F net is equal to ma, and F net in this case is only due to electrical force. So we can say EQ, and this is equal to ma. As I said before, in this case we will ignore gravitational force because gravitational force in the electric field is negligible as compared with electrical force. So that's the reason we are simply saying EQ is equal to ma. So from here we can find out value of acceleration, means vertical acceleration. So this is equal to EQ divided by m. In this case electric field is the same, so both particles, they are in the same electric field. So we can say electric field is the same. Now if we say the charge on proton, let's say charge on proton is Q. So the charge on helium nucleus will be plus 2. If we say the mass of proton is m, so the mass of helium nucleus will be equal to 4m. So in this case simply we can say this is E. So for helium nucleus this charge will be 2q and the mass of helium nucleus is 4m. So we can find out from here that this one will be equal to EQ divided by 2m. EQ divided by 2m. So simply it means that acceleration of helium nucleus, this will be half. So this is A, means this is the acceleration of proton divided by EQ by m. We are saying this is acceleration of the proton, so this will be divided by 2. So from here we have found that acceleration of the helium nucleus, this one is equal to acceleration of the proton divided by 2, means the acceleration is half. If acceleration of helium nucleus is half and we look at the final vertical speed, so final vertical speed will be equal to VV U vertical plus AT, and these two particles, they will spend the same amount of time in the field because the horizontal speed is the same. So time in this case is the same, and initial vertical speed is equal to 0. And if acceleration is half, so it means the speed of the helium nucleus will be half. So we will say the vertical speed of helium nucleus, this will be equal to half of vertical speed of proton. So this is we can find out. So in this case, simply the vertical component of velocity of helium nucleus will be half of vertical component of velocity of proton. So at this point, this velocity will have two components. One is the horizontal component, they have the same horizontal component, and one is the vertical component. This is v vertical, and the velocity v at this point, v will be equal to v square plus vx square. So as vertical component of velocity of helium nucleus is lower, so it means the final speed of helium nucleus also will be lower than the speed of proton at this point. So if we have understanding of these points, we can write down our final answer. So in this case, these points are important. One thing you need to say, acceleration of helium nucleus is lower than acceleration of proton, and both particles, they have the same horizontal component of velocity, because horizontal component of velocity will not change in this case. And also you can say the vertical component of velocity of helium nucleus is also half of vertical component of velocity of proton. So the final velocity of helium nucleus will be lower than the final velocity. If we are talking about magnitude, you can say the final speed will be lower for helium. So these points you need to mention into answer. This is one point, and this one is the second point. This one is third point. And also you have to compare charges and the masses. So you also have to compare this one. So this thing you also need to compare. And after this comparison, you can write down your final beautiful answer. Now let me show you the answer, how you can write down proper answer. So this is how you can write down a proper answer. In the answer, you can talk about helium nucleus. First of all, the comparison. Helium nucleus has double the charge and 4 times the mass. Velocity parallel to the plates remains same, means the horizontal component of velocity remains same because there is no force along horizontal. Electrical force is only acting along vertical, like gravity. Acceleration perpendicular to the plate smaller for helium, so we have seen this one here. So final speed is lower for helium. It's a beautiful question. So if once it is not clear to you, you can do this question again by yourself and then watch this video again. It will make very clear sense to you. For question number 5, it is given to us the two-way switch S is initially at position X. Initially it is at position X. So in this case we have power supply and we have a capacitor. So capacitor will be fully charged after a few seconds. Capacitor will be fully charged. So this is first thing we need to understand. Then it is given to us at time t is equal to 0, switch S is moved to position Y. So it is moved to position Y. So in this case we have the capacitor in this circuit and we have the wire. So capacitor in this case will discharge. So simply we can say capacitor will discharge. For this discharging circuit, for part A1, we need to find out what is initial value of Q naught at time t is equal to 0. Initial value of Q means Q naught. Q naught is equal to the total charge stored on the capacitor, and total charge stored on the capacitor will be equal to C times V. And in this case we have the value of C. Capacitance of the capacitor is given, that is 470 microfarad. And also we have value of V, that is equal to 24 volts. And if we solve this one, our final answer will be equal to 0.011 coulombs up to 2 SF. So this is our final answer because the data given to us has least number of SF, that is equal to 2 SF. So the final answer also should have least number of SF. So the final answer for this one is 0.011 coulomb. So this is our final answer. This question has 2 marks. So the 1 mark in this case will be for writing the formula and you need to plug in the values, and the second mark will be the answer mark. If you got the right answer, you will get 2 marks. If your answer is wrong, you will get 1 C mark if you have written formula and you have plugged in these values. So just basic question, asking you Q at T is equal to 0 means the total charge stored on the capacitor. For the second part, we need to calculate current I naught in wire P at time T is equal to 0. So we need to calculate value of current. Means this is the value of current, that is maximum value. So simple question is asking you to calculate I max. So how we can calculate Imax? Imax in this case will be equal to the potential difference, initial potential difference across the capacitor divided by resistance in the discharging circuit. So initial value of potential difference across the capacitor, this one will be equal to the EMF of the power supply. So simply we will say this is equal to 24 volts divided by resistance in the discharging circuit. So the resistance is 5.6 kilo ohms, means 10 to 3. If we solve this one, our final answer will be equal to 4.3 times 10 to minus 3 amps. So this is the maximum value of current. And current with time, then it will decrease. 4.3 times 10 to minus 3. So this point is very important because initially when we move this switch from X to Y, the potential difference across the capacitor is equal to potential difference across terminals of the power supply. So across power supply means this is equal to EMF of the power supply. So this is how you can answer. For the next part, we need to calculate the time constant tau of the discharging circuit. So simply we need to calculate value of tau, and tau is equal to R times C, and R is the resistance in the discharging circuit. So resistance of discharging circuit. So we can say resistance of discharging circuit. Very important point. Sometimes they can make this one a bit tricky for you. So you need to understand what is this R. Resistance of discharging circuit. So in this case, the resistance of discharging circuit is equal to this. So we have 5.6 times 10 to 3 ohms, and the capacitance of the capacitor, that is equal to 470 times 10 to minus 6. And if we simply multiply this one, our final answer will be equal to 2.6 seconds. So the final answer is 2.6 seconds. And this question has 2 marks. So the 1 mark for this one will be for writing this formula and plugging these values. That mark will be C1, and the final mark will be answer mark. And for this question, there is only 1 mark, so this will be only answer mark. For part 4 on figure 5.2, we need to sketch a line to show the variation with T of the current I in wire E as the capacitor discharges. So this question is about discharging of capacitor, and in your syllabus you also need to understand only discharging of capacitor because charging of capacitor is not part of your syllabus. And for discharging of capacitor, we need to understand how current will change. I as a function of time, this is equal to I naught, means I maximum times e to the power of minus t over RC. Now we also need to understand when I will approach 0. I will approach 0 if t approaches infinity. It simply means that our graph will not touch t-axis. So we will say graph does not touch t-axis. Does not touch t-axis. Or simply we can say there is asymptote. So in this case, this is how you can sketch the graph. This has to be exponential decay, but it should not touch t-axis. So this is how you can sketch. If you sketch this one, you will get 2 marks. One, its gradient has to be negative and decreasing gradient. And second, it should not touch t-axis. So if you sketch graph like this, you will get 2 marks. For part B1, we need to explain why there is an induced EMF across wire Q during the discharge of the capacitor. So first of all, we need to understand when we move this switch from X to Y, this capacitor will start discharging. And when this capacitor is discharging, current in the circuit, in this discharging circuit, or simply you can say current in this wire, this will decrease exponentially with time. So here we have time. So this will decrease exponentially with time, means it will decrease like this. So as current in this wire is decreasing and there is current in the wire, so there is a magnetic field around this wire. So this wire Q is placed inside changing magnetic field of wire B. So it means there is change in the magnetic flux. As there is a change in the magnetic flux, so it means there will be EMF induced in wire Q, because wire Q is placed inside a changing magnetic field. So there is a change in the magnetic flux, or you can simply say is placed inside a decreasing magnetic field. So there is a change in the magnetic field, so there is a change in magnetic flux. So there will be EMF induced. So as current is changing, so simply we can also say as current in this wire is changing, there is a change in magnetic field. And as there is a change in magnetic field, it means that there will be change in flux. As there is a change in the flux, there will be EMF induced in wire Q. So EMF will be induced in wire Q. If you have understanding of these points, so simply you can write down your answer. So the main point you need to understand in this case is that as current in this wire is decreasing, so the magnetic field around wire is also decreasing. So the wire Q is placed inside changing magnetic field. So as the wire is inside a changing magnetic field, so there will be EMF induced in wire Q. So these points you need to understand. Fundamental question about electromagnetic induction, means about Faraday's law and Lenz's law. If you have understanding of these points, so we can write down your answer. So this is how you can write down your final answer. And so you can say current in wire P gives rise to magnetic field, means current in this wire produces its own magnetic field. As current in T changes, or you can say as current in T decreases, wire Q cuts magnetic flux of wire P. Cutting magnetic flux causes induced EMF across wire Q, or you can say changing magnetic flux causes induced EMF across wire Q. So this is how you can write down the answer. If you write down these points, you will get 3 marks. For the second part on figure 5.3, we need to sketch a line to suggest the variation with T of the voltmeter reading V. Means simply question is asking you how this voltmeter reading is changing with time, and this voltmeter reading is depending on current in wire P. And current in wire P, we have already discussed that this is changing exponentially with time. It is decreasing exponentially with time. So we can write down time here as well. Current in P is decreasing exponentially with time. So we can draw the graph like this. And this is decreasing exponentially. So we have current, this is equal to I naught e to the power of minus t over RC. Now we need to understand in this case how EMF is changing. EMF is equal to negative d phi by dt, and EMF is proportional to negative dB by dt, and magnetic field around this wire is proportional to current in wire P. So we can also say that EMF is proportional to negative di by dt. So this is the main point you need to understand. Negative di by dt means EMF is proportional to negative current gradient with time. Negative. As the gradient of this one we can see is negative, and this gradient is decreasing with time. So the EMF has to be positive because EMF is negative of current gradient. So EMF will be positive and EMF will decrease with time. Actually, the shape of EMF and the shape of I against T graph will be the same, because if we have EX and we take the derivative of EX, they are the same. EX and the derivative of EX, they are the same. So this is equal to EX. So it means EX graph and the derivative of EX graph, they have the same shape, because derivative of EX is equal to EX. So if this point is clear to you, then simply you can draw the graph. So these two graphs, they should have the same shape. So simply we can sketch our graph for V here. So this is how V will change with time. So let me draw in a proper way. So we can draw a little bit in a proper way. So you can draw it is somewhat like this. But it should not touch T-axis, because this graph is also not touching T-axis. So when change in current is very small, EMF will be very small. So we can also say here, when current is changing very slowly with time, meaning the change in current is about equal to 0. So the EMF also will be about equal to 0. But EMF will not be 0. So that's the reason it should not touch T-axis. For question number 6, it is given to us figure 6.1 shows a thin slice of semiconducting material used in a Hall probe. Current I passes through the slice in the direction shown. The slice is placed in a uniform magnetic field of flux density V. so that two of its faces are perpendicular to the magnetic field. A steady Hall voltage is developed between the faces PQXY and phase SRYZ. For part A1, use the letters in figure 6.1 to identify the faces that are perpendicular to the magnetic field. Means we need to find out the faces which are perpendicular to the magnetic field. Perpendicular to the magnetic field. And so far, this one simply we can imagine first of all, as this current is passing through this slice, imagine that there is a positive charge. And the force on this positive charge, in this case, if you can find out, then simply you can answer this question. But first of all, we also need to understand, it is given to us that Hall voltage is developed between these two phases. So it's developed between these two phases, PQXY, PQXY. So Hall voltage is developed between this phase, and Hall voltage is developed between SRYZ, between this phase. So it is developed between these two phases. So we can also imagine that this side become more positive. So just you can imagine. So this become more positive and this side become more negative. So it means in this case, magnetic force on the positive charge is to the left. So this is direction of magnetic force. Now simply you need to understand Fleming left-hand rule. Actually, this question is simply about Fleming left-hand rule. For Fleming left-hand rule, you need to understand current is perpendicular to magnetic field, meaning is at right angle to the magnetic field. Current is also at right angle to the magnetic force. And same is true for any. All of them, they are perpendicular to each other. So if this point is clear to you, then simply you can answer this question. So in this case, we have current, so that is into the page. So we can draw this is current, this is into the page. And we have magnetic force in this case. Magnetic force is to the left. So this is direction of the magnetic force. So magnetic force is to the left. Now you can find out direction of magnetic field. So we have said current in this case is into the page. I mean this finger is pointing into the page. And the force, and you can see force is, let me draw like this. So in this case, you see the force is to the left, current is into the page, and the magnetic field is pointing down. Our magnetic field will be pointing up if this side is positive. If this side is positive, then magnetic field will be pointing up. Magnetic field will be pointing up. So let me write on the second situation. Current is into the page. If the magnetic force is to the right, so this will be easy for you to understand. So in this case, current is into the page. And the magnetic force, you can see, is to the right. So the magnetic field is pointing up. And vice versa is also true. If force is to the left, force is to the left, so the magnetic field will be down. And so it means direction of the magnetic field is vertically up or vertically down. So the magnetic field is perpendicular to these two faces. So we can say this face, this top face, this face is perpendicular to this face, perpendicular to this face, and this face is PQRS. PQRS. So magnetic field is vertically down, or you can say is pointing vertically up. So it is perpendicular to PQRS. So you can say PQRS and WXYZ. So this is W, this is X, this is YZ. So magnetic field is perpendicular to these two faces. So let me explain in a better way. So you can imagine that this is the box. So magnetic field is like this. So it is perpendicular to this face and also perpendicular to this bottom face. So magnetic field is like this. Our magnetic field can be like this because we don't have exact direction of magnetic field, but magnetic field is along vertical. So if this point is clear to you, then this question is very straightforward one. You can look at this question, you can find out. So we can simply write down this will be W, X, Y, Z. For the second part, we need to explain how the steady Hall voltage is developed between phases PQXY and SRYZ. Between phase PQXY, mean between this phase and this phase, how this is developed. You can also imagine in this case, if you connect a voltmeter here, you will read reading on voltmeter. And this voltmeter reading is the Hall voltage. Now we need to explain how this Hall voltage is developed. Steady Hall voltage. Steady means constant, means when it has reached maximum value, Hall voltage will be constant. So for this purpose, we need to understand initially when current will flow, imagine that there is a positive charge here. This positive charge will experience a magnetic force, because in this case the magnetic field is vertically downwards or is vertically upwards. So we can imagine in this case magnetic field is vertically upwards. So I will draw just one arrow. Imagine that magnetic field is vertically upwards like this. It's vertically upward. If the magnetic field is vertically upwards and current is into the page, so the positive charge will experience force to the right. So positive charge will experience force to the right. So this side will be more positive. So this side will be more positive and this side will be more negative. Now I will simply clear this arrow now to show you the forces acting on this charge. So initially the force acting on this charge will be only magnetic force that will be acting this way. So this is the magnetic force. But as more and more positive charges accumulate on this side, there will be more negative on this side. So there will be electric field between these two faces. So there will be electric field from positive negative. So I will just draw these big arrows. So there will be electric field. So this is direction of electric field. Simply you can imagine just one arrow we have drawn. So this one arrow is telling you direction of electric field. So the electric field will be this way. So as electric field is pointing to the left, so this positive charge, it will experience electric force also to the left. And one stage will come after a very short period of time. We will see these two forces are equal. Electric force will balance magnetic force. So this one is the electric force. So let me use different color. So electric force. So this force is electrical force. After small amount of time, short amount of time, FB will be equal to FE, electric force. So when these two forces are equal, then current will just flow in a straight line. So it will just flow in a straight line. Means charges, they will not be deflected towards positive plate or towards negative plate. And at that point, this Hall voltage, this will have reached the maximum value, or we can say this Hall voltage will be constant, or you can say this will be steady, or you can say it has reached the maximum value. So you have to understand only these points. If you have this understanding now, then you can write down the answer. So let me show you the answer, how you can answer this problem. So in your answer, you can mention these points. Force on charge carriers is perpendicular to both magnetic field and current. We have already discussed, according to Fleming-Lefton rule, force has to be perpendicular to the magnetic field. Force also has to be perpendicular to current. Very important point. Current has to be perpendicular to the force. Current also has to be perpendicular to the magnetic field. And this is also true for the magnetic field. Magnetic field perpendicular to current and also perpendicular to force. So very important point. In the last part, they were checking your understanding of this point. And next one, you can say as charge carriers are deflected to one side and electric field is set up. As we have discussed, there is an electric field that is set up between these two faces. Steady VH when electric and magnetic forces on charge carriers are equal and opposite. Then charges just move in a straight line. So they will not deflect. Initially they will deflect. So when they go, they will deflect one side because magnetic force is stronger. But as time will pass, electric field will also get stronger. When electric force is getting stronger, so there will be less and less net force on positive charges. And at one point, two forces will be balanced. So then charges will just go in a straight line. And at that point, value for Hall voltage will be maximum. And that value is steady Hall voltage. For part D, it is given to us the magnitude of VH is given by the equation. Means VH is equal to Pi over NTQ. And for part D1, we need to state the meaning of the symbols N, T, and Q. You may refer to the letters in figure 6.1. So first of all is N. N is the number density of charge carriers, mean number of charge carriers per unit volume. So we can say this is number density of charge carriers. So this is one point you can write down. Number density of charge carriers. And T is the thickness. T is thickness. thickness, and this is thickness of the side through which magnetic field is passing. So magnetic field in this case is passing through PW. So we can say this is thickness PW, or you can say this is thickness SZ, or you can say RY, or you can say this is RY. Means the thickness through which magnetic field is passing. So in this case magnetic field is vertically, so it is passing through this thickness, we can say this thickness. So this one is a T. And the last one is Q. Q is the charge on charge carriers. Charge on each charge carrier. So this is charge on each charge carrier. So if you write down these 3 points, you will get 3 marks. Now let's go to the second part. For the second part, we need to suggest with reference to the equation, means we have to use this equation. Why the slice of the material used in a Hall voltage, Hall probe is thin. So for that purpose, simply you can understand, if we make T small, means this T becomes small. So the VH will be large. So if the VH is large, so it is easy to measure. So that simply you need to write down. So we will say in this case, if T is smaller, means the slice is thinner, it means Hall voltage produced will be larger. So it will be easy to measure with higher accuracy and lower percentage uncertainty. With higher accuracy, simply you can say. So these points you have to mention. So let me show you the answer. So in your answer, so you can mention these points. So you can say simply in this case, VH is proportional to T. Actually, this is inversely proportional to T. So you can say VH is inversely, if you want to say in a proper way. So is inversely proportional to T. So T needs to be small for VH to be large enough to measure. So if T is small, VH will be large. So we can measure VH with a higher accuracy, or you can say with lower percentage uncertainty. So these points we have to mention. If you mention these points in your answer, you will get 2 marks. So this is also the answer for part A. Even if you write down VH is proportional to, that is acceptable, because they are proportional mean it is inversely or directly proportional. So, but if you want to be very specific, you can also say VH is inversely proportional to T. So if the T is small, VH will be larger. And if VH is larger, it means we can reduce percentage uncertainty, or we can measure this one with higher accuracy. And that's all for today's video. I hope you have some better understanding of these topics. And if you have any questions, please leave your questions in comments and I will be answering as soon as possible.